kind of get our brains around this, a student is going to throw the ball straight up. Somebody's going to take their timer and they're going to time how long it takes to go up and then back, or just up and stop, right? And then I'm going to throw it again so that it goes higher. Can you close the door for me? Thanks. If I throw it so it goes higher, the student says it will take more time to get there, okay? So my task for you is to figure out, first of all, do you agree with that? And then secondly, and the more deeper part of that is why, right? Like, what is the physics behind it? We got to start somewhere, so let's start with a vote. Raise your hand if yes, I agree with that student. I think that is correct, that it's going to take more time to go up if it goes higher. Raise your hand if you disagree with the student, you think they're not quite there, there's something wrong. And it's okay if you don't vote. I had a conversation with the last class, and I'm going to read it. You guys can put your hands down right now, because I think that we're into a point in physics where we're getting to stuff that's hard, and it's kind of hard to think about. And for some of you, and I'm not saying all of you, but for some of you, it's really scary to be wrong. It's really scary to admit that you don't know something. But I want to let you know, number one, this is a safe place, right? We talked about this yesterday. And number two, that I want to make sure that you're willing to share that stuff, because if you don't share your ideas, you're never going to know if they're right or wrong, and you're not going to learn the stuff as a result. Does that make sense? So moving forward, as we keep going through this class, I want you to make a commitment to try to come up with an answer, whether it's right or wrong, and be open to figuring out whether it's right or wrong and why. That's the whole idea that we're going for. Okay? So if we take a look at this, and if we take a look at what's happening here, we said some people said yes, some people said no, we're not quite sure. I'm going to suggest that we graph it. Oh, did you see there's a cute little picture of a student throwing a ball in the air and kicking their feet up, which I think is kind of adorable. Actually, before I graph anything, question for you. What do you know about the velocity with which I will have to release the ball in order to make it go higher?
Yeah, 2 once.
I heard like two things simultaneously, but I couldn't tell. What did you say?
The velocity would have to go up.
Does that make sense to you? If I'm going to throw the ball to a higher height, I'm going to have to throw it with more velocity. Does that seem pretty logical? Okay, I want to make sure that makes sense to you. We will verify that in this process, but I just want to make sure that makes sense. So if I throw the ball so that it goes to a higher height, really, it kind of makes sense to us that we're going to have a higher initial velocity as well. The reason I wanted to say that was because I want to graph things on a velocity versus time graph, because, velocity versus time graphs can tell you so much. So if you haven't yet written anything down or got any piece of paper, I want you to write this down right now. Just to and it can be on the side. I don't really care where it is, okay? But go ahead and write that down. And then what I'm going to ask you to do is to draw a graph or sketch a graph of the velocity versus time of the ball from when it's released from my hand to when it gets to the top. Okay? Hint, we talked about this yesterday. Okay? We talked about this yesterday. Draw a velocity versus time graph of the ball from when it leaves my hand to when it gets to the very top of its path. Okay? If you don't know, or you do, try and talk to your table mates. I want you to write something down. Give it a shot. If you have your notes from yesterday and you want to look at those, that's not a bad idea either. But go ahead and try and draw that. What is that going to look like? Velocity versus time graph. Give it a shot. Here we go. Let's do it. What did you say? What does the graph look like from when it leaves my hand to when it gets to the top of its path? Unto what?
Negative slope.
Negative slope. Where does it start?
Positive.
Up on the positive.
Up on the positive. Why does it start up here? Because I threw what?
You're throwing it at a positive velocity. Going up.
Yeah, I'm giving it it's going up, right? Positive velocity is moving in an upward direction, so it starts off positive, and then you said it goes down at a slope like this, bam, something like that? Yeah? Hey, quick question before we go on. What does this slope represent?
Speed of the ball.
A decrease in the speed and the, what did you say?
Accelerate.
No, you're absolutely right. That's what I'm asking.
Decrease of the acceleration. Acceleration.
It's a decrease of the speed, and the slope can tell you the acceleration. Are you with me there? Okay, so I just want to make sure that makes sense. And then this point, why did I stop my graph right here?
Talking about going up.
That's the maximum height, that's where it stops, right? Velocity of 0. Okay, so now that we've got this graph, my line is not perfectly linear. I'm going to try and make it a little bit better of a line. Maybe it's like that. Anyway, you get the idea. Now my task for you, with your table mates, is to draw another line on the same graph, and you know what I do, like a dotted line or something like that, just so we don't get confused, representing this second flow with a higher initial velocity. Okay? Same graph, so just put another line or whatever on this graph that represents me throwing it with, oops, I was about to hit that thing, with a higher initial velocity than the first one. Okay? Go ahead and do that. Give it a shot. Talk to each other. Friends, I am so excited about of this conversation. So let's come back together here. So to draw this second part of your graph, where is it starting? Where does the next line start? Higher up? Why is it so higher up? Higher velocity, right? So I got a higher velocity up here, so we'll put it up here. And then, oh, it's frozen. You can't see it, there it is. What's going to happen to that line? It starts higher up. What do you know about the slope of the pink line as compared to the slope that the blue line will have? Same? I hear somebody say same. Why?
Because gravity is acting on both of the lines the same.
So different thing, but yeah. Gravity is acting the same on both of them, right? It's not like when I throw it with a little bit of velocity, when I throw it a lot of velocity, that the gravity changes. Okay? We haven't dug into exactly why gravity works the way it does, but I hope that in your brain and in your gut it makes sense that the gravitational acceleration is going to be the same in both cases. So we can see then, if I draw this, I'm going to kind of draw it as a dotted line. I'm trying to draw it parallel because it has the same slope. Okay? That's really not very pretty, I apologize. But you get the idea, right? Parallel line, is it going to take more time? Oh my gosh, it is! Now, a lot of you had a gut feeling that told you, yes, that it was going to take more time to get there. But the reason I love this is because now you've got physics to prove it. You've got physics to back it up, not just, I think it's right. You're like, I know it's right. Okay? We just did it. Now, one more thing, because we kind of made this statement that if it goes higher, it'll have a higher initial velocity. Question. Do you know how to find the displacement that it goes higher from a velocity versus time graph? Do you remember how to do that? No, you're right. Keep talking.
Good.
Oh, then you got all the right answers, so that's what I'm saying. It's not the slope, it's the what of the graph. Starts with A.
Acceleration.
No, wrong one. It's the area. Does that make sense? When you're finding the displacement, you're looking for the area. Take a look at this, you guys. Here's the area of the blue one. Here's the area of the pink one. Which one's bigger? The blue one has a bigger area. That means the blue one traveled farther. So you've got all of that stuff wrapped up in this cute little graph here. You see what I'm saying? It's a beautiful thing, right? Okay. Now, I want to take this a step further. So yesterday, when we were doing our warm-up problem that lasted pretty much the entire period, one of the conversations that we had to do with whether or not this line was straight when it started going back down, or whether or not the slope changed. Do you remember this? And we kind of left it there, and I was struggling because it's really hard for me to just use words to convince you that that's true. If you've got it stuck in your brain so much that it's got to change, then any words I tell you are not really going to work. So I came up with an idea, and I wanted to share it with you. So instead of just talking at you about it, I'm going to try it, okay? So I'm going to do it, and I actually did, and I'll show you just in a second. I took a ball, and I threw it in the air, and then I went like this, and I graphed its velocity versus time, okay? I graphed its velocity, and I'll show you in just a second what that looks like, but my question for you is, what is going to convince you on a velocity versus time graph where you know, because we just said it, that this is what it looks like as it's going up? What is going to convince you, my friends, whether you were skeptical or not, you can still answer the question, that the acceleration is the same on the way down? What about my velocity versus time graph would convince you of that? That it has the same acceleration? What part of a velocity versus time graph tells you the acceleration? The slope, right? So if I can demonstrate to you that the slope stays the same, you with me there? Then that would mean that the acceleration stays the same. Fair? So I did this, we tried it yesterday and it didn't quite work, and we tried it this morning and it worked, except that you have to either flip your head over and stand on your head, okay, because the video got flipped over, or you have to like switch your brain a little bit, because I was doing it fast and I didn't have time to play with it too much. So I'm going to find it here quick for you. And I used some software that we will use soon, but we're not quite there yet, so I'm going to just show this to you. So this is Miss Coleman standing on her head, and or the video just got flipped, okay? And I'm standing right outside there, and I'm going to throw the tennis ball in the air. You can watch, I'll show you the video here real quick so you can see it. Oops. No, what are we doing here, friends? Okay, oh, hello, go away. I don't know what this is. I just wanted to go away and do physics. Okay, here we go. See if I can do this without messing things up. Here we go. So I'm going to push play, and you can watch the video, maybe. Come on, team. Oh, what is this? Go away. Okay. Up and down. See with me there that it's going up and then down? Do you all see that? Okay, so again, you can stand on your head. Oh, and then it bounces back up. And I got it, yes! All right. So, again, you can sit it, you can look at it upside down, or you can just, flip your head over. Either one works. All right, so here's my position versus time graph. The really nice thing about this software is that I just put dots where that ball was, and I can find the position versus time graph. Does it surprise you that it's a parabola? No? The parabolas that we've been drawing have been flipped over the other way. But remember that this is all flipped over because my video got flipped over, right? So this, again, if you flip your head this way, then it's the parabola like we're used to seeing. We good? Okay, so that's not going to convince you of much because that's just a parabola, and that's just a position graph. Remember, I just suggested to you that the thing we really needed was the velocity graph, right? So we're going to take a look at the velocity graph next. So I go here, and I've got my velocity graph right there. Okay? So it's not like the dots are not exactly perfect, but because we're doing an experiment, right? So it's not exactly perfect. But what do you notice about the slope of this line, friends?
It's positive.
It's positive. Why is it positive? So I have to sit on my head, right? Because it's all upside down. Does that make sense? Yeah. So I appreciate the fact that you're noticing that, but again, remembering that it's upside down, which is why it should be, this is positive, even though we know it should be negative because it's going, the acceleration goes down. So good call. Not only is it positive, should be negative, but is it changing? Is the slope changing? It is not. You with me here? Okay. I hope that if yesterday you were feeling a little skeptical or feeling a little unsure, that this can help you to see that that slope does not change. And if the slope does not change, that means that the acceleration does not change. So it doesn't matter if my object is going up or going down. The acceleration is always pulling down the same amount. Okay? So far, so good?
What would the acceleration versus time graph look like?
Well, that's a great question. I'm super glad you asked. So if we drew, here, I'm going to go back to just our regular graphs. So our velocity versus time graph really should look like this, right, if we're not flipped over. So if it looks like this, what would the acceleration versus time graph look like, guys? So we're looking at the slope, right? The slope of a velocity versus time graph is going to tell us the values for the acceleration graph. So the slope is negative and constant, which means that the acceleration is negative and constant. Just like that. That's an awesome question. Thank you for asking. Yeah. How are we doing? We okay? Okay. So I'm just kind of keeping an eye on time here. So you remember last Friday, we dropped the puppies and we dropped the tennis balls and we took some measurements. And then we were going to do some lab analysis. And we may or may not have started that. I don't even remember. But the long and short of it from the other two classes was, and maybe you guys are an outlier, but their data was pretty big. And I think it was just because I rushed you guys through it super fast. Okay? So what I'm going to do is I pulled some data from the class averages that we got, and I want to show you what I found from that data. Okay? Just so that we can kind of move fast and get to where we need to get next. So I pulled some data. Actually, I didn't pull it. I should give credit to the person who deserves it, right? Mr. Gribble got this data. And right, so yeah, right. All right. So we pulled heights and we converted them into meters appropriately. We put the times, and we graphed it, and we got this kind of like thing that it's really hard to tell, but if you get good data of height versus time, it's not going to be a straight line. Okay? So even this is, it shouldn't be a straight line, but it's not, it shouldn't look quite that nasty. So then we did some clever physics, and just given our time and our opportunity, I'm not going to belabor it because it's not something I'm going to test here, but it's not something that's on a standard. It's just kind of clever stuff, and we'll come back to it another time. But it's kind of neat that you can see that if you graph height and the square of time, well, why would you do that to make it a straight line? You can get something that looks a little bit, it should be more like a straight line. And that straight line, from that straight line, we can find out what the value of the acceleration is. So I think in the last few days that we've been talking, I'm hoping that I've convinced you that the acceleration is constant. Okay? And that it's constant for anything that I throw in the air, or anything that I let drop, or anything that I throw in the air and let drop. Okay? And that value is one that we're going to write down and talk about. So most of you have notes out. If you don't, this is the time to get them out. If you do, this is the time to put a new little header on things, because we are going to add some new information today. Okay? Today our concept and discussion is about solving freefall problems. And in order to do that, we have to know what freefall is, right? Yeah. So have you heard of the term freefall? Do you have any idea what that means? I've kind of said it a few times without really telling you anything about it. Does anybody know what freefall means? Yeah.
It's just when you basically just let go and just have it fall.
Yeah. When you let go of an object and let it fall. It is in freefall, right? How many of you have ever ridden the, what is it called eventually, the big tower?
Tower shot.
Space shot, yeah. There are lots of them at different parks, and I just couldn't remember. So space shot, but tower chair is the same thing. That's not the one adventure. They all take you up in the air, and then like you look and you're like, oh, it's so pretty, and then all of a sudden, what happens? You drop. And when you drop, your belly starts to get a little goofy, right? You're like, woo! The reason is because you're in free fall, right? The only thing that is acting on you, the only thing that's pulling on you and accelerating you is what? Gravity. That's it. So free fall is a situation where gravity is the only, I'm not going to use any fancy words here, I'm just going to say the only thing causing an acceleration. On an object. And we'll get into the why and how later, but for right now I'm just going to tell you that. Now I have a quick question though, before we move on too far. When I throw my tennis ball in the air, is it in free fall on the way up?
No.
Based on this definition?
No.
Is the ball accelerating?
Yes.
Yes. What's causing the acceleration?
You.
After I let it go, what's causing the acceleration?
Gravity.
Gravity. that's causing that acceleration. Are you with me there? So even though it's going up, because I let go of it, the only thing that's causing the acceleration is that of gravity. So really, it's things going up and going down, things moving in this dimension, in the vertical direction, okay? Free fall, so we're talking about objects moving in the vertical direction. It is a little misleading. I agree. We should write a letter to somebody. I don't know who we write the letter to, though. Yeah. Okay? Objects moving in the vertical direction. So we have displacements that are going up and down in this way. We're not talking horizontal anymore. We've done the horizontal, guys. You guys rocked the horizontal, I think. I haven't graded the test, but I'm thinking. Yeah, so we did that. Now we're talking up and down. Vertical direction. Vertical displacement means that we're always going to talk about a delta, not a delta x anymore. It's a what? Delta y, yeah. Okay? Bless you. And the acceleration that it's experiencing is always the same. We've just kind of picked at that a little bit. The acceleration that it's experiencing has a very special value. I call it A sub g because the acceleration is due to gravity. Does anybody know what that value is?
9.8 meters per second.
It is. It is. Now, if you didn't know that, there's a face like, how would I know that? Well, it's okay if you don't. I will tell you where you could find it. 9.8 meters per second squared. And oh, by the way, gravity's always pulling which way? Down. So I'm going to put a what there? Negative sign. That negative sign matters. Now, if memorizing numbers is not your thing, that's totally fine. If you look carefully at your equation sheet, in fact, go ahead and pull out your equation sheet because we're going to need it in a second. Okay? On that equation sheet, top left-hand box, you know, you've got your equations on the very left side, but then there's that middle stuff. And if you haven't looked carefully at it, you can take a look. There is one, it says G, but I like to use A sub G. And it says 9.81 right there. Now, do I like the one? I don't, just because I'm lazy now, I have to write an extra digit. I'm going to use 9.8. If it makes you, like, if you're like a rule follower and you really like to put that extra piece in there, you can totally do that, okay? 9.8 meters per second squared. How are we doing? Are we okay so far?
Which box is what?
It is in the top left-hand box. We're still up there, top left-hand box. But it's in the right column. Do you see what it says? Yes. Thank you for asking and checking. I appreciate that. All right. Questions so far? Same question? What does it say right after the 9.8 meters per second? Does that make sense? Yes. It's a very good question. So let me clarify that for everybody. You just notice that on the equation sheet, it doesn't say negative 9.8. It says 9.81 meters per second. But there's another word back there. It says down, right? And the negative means down. If you put the negative and you put down, then it would mean up, and that would be really confusing, right? It would be double negative. We really let those like forever ago. Okay, so that's the deal. So here's the thing. Is that this free fall business seems a little weird, seems a little new. We've got gravity acting. There are things that are moving in the vertical direction instead of horizontal. But friends, it's really not that bad, and let me tell you why. It's not bad because you have those 4 equations that we spent a lot of time on last week. Do you remember? We use the same 4 equations. Okay? We're going to use the same acceleration equations that we've been using for the last week or so. Okay? Nothing new. It's all the same process. Or you can use a graphical method. The only thing that's different is that every single time your acceleration is already given to you. Okay? Now this acceleration is not constant forever and everywhere in the universe. This acceleration is true at the surface of the Earth near sea level. Okay? If you go up to the top of Mount Everest, the acceleration of gravity will be not 9.8, it'll be less than that. Okay? If you go down to the bottom of Death Valley, the acceleration of gravity will be a little bit more than 9.8. Okay? But on average, 9.8 is the value we're going to use. And so that's just going to be constant. Now, if you have a problem that talks about the moon or talks about another planet or something like that, then you'll have to look at it, but it will either ask for it or tell you.
What is
Okay.
this?
It's a sixth of that, so 9.8 divided by 6. Yeah, I can't recite it to you off the top of my head, but you can figure it out. You have a calculator, don't you? No, not yet. Get it out because you need it. All right. Speaking of needing a calculator, why is he going to need a calculator? Because we're going to do some practice. Here it comes. I know. AJ, did you have a question, Ray?
No.
Okay. Yeah.
1.6 meters per second squared.
Bam. There you go.
Everyone?
Question.
Pass them out to the class.
Use the first equation. The difference is 1/2.
So you can still use that, it just, you wouldn't plug in an acceleration. So often you won't use that one because it's kind of like a free given. Yeah. All right, physicists. So we've got just a few minutes. I want to do a little practice because this is what your homework's over and I want to make sure that you're ready to go. Okay? You do not have to copy these problems down. You can just note that they're on page 62 of your textbook. This is question number 2. Okay? So you don't have to write it down, you have to copy it down, but if you write down your answers, then you can look back and say, oh, it was on that question. Okay? So here we go. I'm going to solve this first one at least using an equation. So you can do all of this graphically as well, and if you'd like me to show you, I'm super happy to do that. I'll probably throw a couple of them on Canvas just so you can see, but for right now I'm just going to do this algebraically, which means that I'm going to start with my always, right? I'm going to start with my givens. Before I do that, I guess I probably should read the question, though. That usually seems to help. All right, it says, a flower pot falls from a windowsill 25 meters above the sidewalk. I'm going to do part A to start. How fast is the flower pot moving when it strikes the ground? Now, sometimes it's hard to kind of conceptualize these, so I'm going to go and draw myself a little flower pot. There it is. And I'll put flour in it because, it seems like a flower pot should have flour in it. There we go. And I'll put it on a windowsill and put a street below. And this is obviously not drawn to scale. And this is 25 meters above the ground. Okay? So just to kind of give you a concept of what's going on. What have you got for a given? Raise your hand if you can tell me a given. Go ahead, what you got?
25 meters.
25 meters. So then what's the next question I'm going to ask you? I would ask, what is that, right? Yeah. So it is 25 meters is absolutely given, but I want to know what it is. It says meters. So what's it going to be? It's a change in position or a displacement, and because we're going up and down, we're going to call it y. Quick question for you. Is the flower pot going up in the air, up in the positive direction, or is it going down in the negative direction? It's going down, which means that we need to have a what in front of that 25? Negative. That negative matters. Make sure you include it. All right. So the nice thing about having or volunteering to give the first given is that you get to pick whichever one is the easiest to find. Right? I want some more givens. I need at least 3 so I can have an unknown. What you got?
Would the acceleration be the negative 9 point?
Yes. So that's the hidden given that's always here when we're talking about freefall problems. If something is falling in the vertical direction, we're going to have an acceleration of negative 9.8 meters per second squared. All right, 2 down. I need 1 more. There's another hidden given in there. What's what you got?
The initial velocity would be 0.
Why do you think the initial velocity is 0?
Starts at rest.
Yeah, and there's no reason to think it doesn't, right? It doesn't say that somebody was having a tuffle and threw it down, or that they threw it up in the air to see what's going to, it does. It starts at rest. Okay. So those are my givens. And then my unknown, what is the thing that I'm looking for?
Final velocity.
Yep, it says how fast is it going when it strikes the ground, so that is going to be the final velocity. Okay? The process is exactly the same as it was for the problems that you did for the quiz on whatever day you took it, I can't remember. But, so take a look at your equations, talk to your table mates, find the appropriate equation that goes with these 4 variables. Go, go, go. We are not given the time, nor do we care. All right. Did you guys pick a good equation? I hope so. I just thought it was cute the way you said that. Which equation did you choose of those four? The last one, the one on the bottom there. So you have VF squared equals VI squared plus 2A. I'm going to write it as delta Y. I know that in the equation sheet it says delta X, but it's delta Y because we're going up and down. Anything we can get rid of to make our life a little easier?
VI.
What do I get rid of? VI? Because it's 0? And then to solve for VF, I just have to do what? How do I undo a squared? What? Okay, thank you. Take the square root of, so it's going to be 2 times A times delta Y. Oops, delta Y. Okay? And then you can go and plug in your numbers. If you don't have a calculator, go ahead and get one out so you can check it. Or not check it, but plug it in. So square root of 2 times negative 9.8 meters per second squared. Now you may see why it's really important that we note that it's 25 meters down or negative 25. Because otherwise we've got a square of a negative number and that makes your calculator explode. And or it's just an imaginary number which doesn't help us for anything. Did you get a value?
22.14.
What was that?
22.14.
22.14.
Meters per second.
Do you guys agree with that? And I was just about to ask, thank you for answering without me even saying it. Meters per second. Okay? How are we doing? We okay? If you got that one, try part B. How much time does a passerby on the sidewalk below have to move out of the way before the flower pot hits the ground? Same set of givens, but now my unknown is what? Is the time. Okay? So I've got delta Y, A, VI, and T. I would not use my VF. The only reason I say that is because if you messed up VF, then your answer might not make sense. So it's always a better choice to pick or to use the givens that you know for sure, if at all possible. Can you find an equation here? The big one? Ms. Carbling's favorite? It might look scary at first, but it's not bad. Especially when you look to see if there's anything goes to 0. Does anything go to 0?
Yeah.
VI goes to 0, doesn't it? See you later. I need to solve this for T. So when I solve it for T, I get 2 delta Y over A. Okay, does anybody want me to go through the algebra there?
Yeah.
Okay, just want to make sure. I didn't want to waste my time. I just want to make sure. So I've got delta Y is equal to 1/2 AT squared. I'm multiplying by 1/2, which is like dividing by 2. How do I undo dividing by 2? How do I do it? Multiply by 2. Divide by A. Oop. If you guys need to see that homework, it's here up here again. Sorry. I will put answers to that problem and the other one up on Canvas today. Okay? Have an awesome day, you guys. A great weekend. Be safe. Make good choices. Wear blue on Monday. Or on Tuesday. Excuse me, on Tuesday.